Okay, so here we've got a empirical formula C₂H₃, and we've been given the molar mass of the molecule, and we've been asked to work out what the molecular formula is, right? Okay, so how would I approach this? Well, one of the first things I would do is kind of think about, well, what's the empirical formula? What's the molecular formula, right? So the empirical formula would be the smallest whole number ratio of the atoms of each element present in the compound. And we've been given that empirical formula in the question. And okay, so for molecular formula, what would that be? So molecular formula, rather than being some sort of simplest whole number ratio, it's the actual number of atoms of each element present in the compound, right? So that it shows us the actual number of atoms of each present. Okay, so given that, how do we navigate this? Well, we've got the molar mass of the molecule, but what we don't have is the molar mass of the actual empirical formula. Why would that be useful? Well, if we have the molar mass of the empirical formula, we can compare that with the molar mass of the molecular formula, figure out what the difference is, if there is one, and appropriately scale up our empirical formula to get to the molecular formula. So that is in effect what I'm going to do in this question. But how do I get to our molecular formula for the empirical formula? Well, I'm going to use the periodic table to help me with this, although given the elements we're dealing with, you may already actually know what values you kind of need from the periodic table. But what we're looking for is the molar mass that would be attributable to the carbons and the molar mass that would be attributable to the hydrogens. And in effect, how we're going to do this is using the relative atomic masses of those elements, right? So the relative atomic mass of hydrogen we've got here, and of carbon we've got that here as well, right? So for carbon, our relative atomic mass is 12, and for hydrogen, our relative atomic mass is 1, right? So these are effectively our molar masses. So I'm going to just put a note with regards to those, just to kind of articulate my reasoning in writing. So the molar mass for the carbon is going to be equal to 12.0 grams per mole, right? And our molar mass for the hydrogen is going to be effectively 1.0, as you can see here, 1.0 grams per mole, right? Okay, so given we've got these values, all effectively I need to do is multiply them by their respective coefficients. So how many times they occur in the formula, and add up those for each of the elements. So in this case, for carbon, we've got 12 times, and you can see the coefficient here is 2, right? It's 12 times 2. Plus for hydrogen, we've got 1 times, and then the coefficient, which you can see, is 3. So 1 times 3, right? And then we just add that up, right? Okay, so if you had to go adding that up, what you should have come up with is 27, right? So therefore, what we can say is effectively, so that's equal to 27. Therefore, the MR of C₂H₃ is equal to 27 grams per mole, right? Now that 27 is what we effectively have now, which we didn't have at the start, is we have a molar mass now for our empirical formula, and we have what's given in the question, the molar mass, the 189, the molar mass for our actual molecule, right? So effectively, this gives us an opportunity to say, well, if we can figure out the scale factor, effectively the multiplier between the empirical and the molecular, we can effectively use that to work out, well, what's our molecular formula. So the equation I'm going to effectively use for this stage would be that the multiplier is equal to the molar mass of the molecular formula. So I just put MR molecular divided by the MR of the empirical formula. So I'll just put MR empirical, okay? Now, if we do that, in this question, we're going to have 189 divided by 27, right? And that effectively is going to be, well, if you have a go, actually, before, if you have a go, see what you get, but that is going to give us 7, okay? Okay, so now that we know that, what we can do is now use this multiplier, right? So the multiplier is 7, which effectively means, 7x, right? 7x, multiply 7x. We can use this with our empirical formula to come up with the molecular formula. So for carbon, as you saw, it's C₂H₃, so it's carbon, we're going to have 2 times 7, right? And if you do that, what you find is that obviously that's 14, and therefore we can say for the carbon in the molecular formula it's going to be C14, right? Now for hydrogen, what we're going to have is, obviously it was H3, right? So we're going to have 3 times 7, right? And that's equal to 21, right? So in the case of hydrogen, we effectively know that we're going to have H21, right? And so if we now consolidate that, we find we get the C14, H21, okay? And that is in effect, in this case, our molecular formula, right? Now C14H21, okay, that, I mean, this molecule, if we actually look at a molecule in an actual molecule which has this molecular formula, just as for example purposes, for what I've got here is I've got a molecule, octyl benzene, okay, and I've also got an octyl benzene radical. It's not, octyl benzene radical is not like a IUPAC name for it, but this is just just a general name I've given here, just to kind of illustrate what we've got here. And if you do count the hydrogens in the octyl benzene, you would find that you're going to get C14H22, right, if you count these hydrogens. And over here with the octyl benzene radical, as you can see, one of the hydrogens has been knocked off, so you've got an unpaired electron in the place of where the hydrogen previously was. So because you've got one less, obviously it's going to be, instead of C14H22, it's going to be C14H21. So you can imagine perhaps this is something which you could get after certain steps in a radical substitution reaction, right? So this obviously matches the molecular formula that we had previously determined, the radical. Now octyl benzene is actually used in industry. It's not, it's used as a solvent. It's not necessarily the most popular solvent, but it is used as a solvent. And I'm not going to go into too much detail about it because it's not necessarily the main focus of the video. But this would be something described as a non-polar solvent. And it has, because it's a non-polar solvent, it has specific properties and behavior during reactions which make it quite suitable for certain kinds of reactions. But you can feel free to look into that, look into non-polar solvents, etc. Okay.